Three graphs, straight line and volume ones. Which one, Zed? Zed, are you able to unmute yourself now? Just check, or is your mic still not working? Otherwise, you can type. That's okay. No, Zed, you're still unaudible. Okay, you type it. You type it only. I'll read it. I'll give you back, both of you, Wafi and Zed. Are your exams over? UT, are they over now? Your summer vacations have started by now, because I think most probably July you people will be having your summer vacations. So summer vacation has started there. And what about you, Wafia?
Our PT1 exam completed and summer vacation starts on next month starting.
July. So you have your vacations on July. Okay. So in the month of July, I'll be taking your extra classes as well. See, because we are here in this chapter potential. So you have to be right now on at least current electricity in the middle portion. So that's why I'll be giving you backup also, and we'll be having extra classes. So let your exams begin. Okay, your vacation will be over by 10 July. Doesn't matter, Zad. It's okay. It's okay. We'll have the class. 10 July, it's getting over. No, so we'll have the classes prior to it. Fridays you have off. I'll take your extra classes on Friday. So don't worry about that. All right. So Rifat Reem, your exams are over now?
Yes, ma'am.
Reem, yours are over. And what about you, Rifat? Rifat, it's over. Okay, fine. All right. Okay. So, Zaid and Wafia, see, we have completed chapter 1 and we are on the chapter 2, in the middle portion of chapter 2. Means we need one more class for completion of potential, then we'll be over with this chapter. So I'll give you the backup of the previous classes, but I think you should continue from now onwards. From here, you'll be able to understand. Basic terms I've told you about electric field, if you remember those graphs that Zaid you were mentioning. Electric field we have already discussed, so that will be used. That will be utilized, so you'll be able to understand. One more term, that is their potential. So in this, there's a relation between electric field and potential. When we'll do potential, you will be understanding it better. In short, I'll tell you, whatever you have studied it for electric field, no, everything that is similar for potential in case of scalar form. Electric field was what? Electric field was a vector quantity. You needed directions for it. All the directions were different. Then you used parallelogram law and every law to solve all those vector quantities. It's just that potential is the scalar form of it. So, and you can, one more definition of potential is there, that is the work done, that is done by moving a unit positive test charge from infinity to a particular point. All right. Now, there is one relation between electric field and potential, and this is given in your NCERT clearly. So this is an important point. Derivation also comes, and those 2 points which I'll tell you, those 2 points also come. So there's one relation between electric field and potential. I think Zaid, you should continue in this batch. Were you by mistake on the previous one? Will you, I think because this batch is suitable for you. Because in the previous batch, the topic is ahead. Okay, Zaid. So you can continue in this batch. This will be suitable for you. So relation between electric field and potential. See, okay. All right, Zaid. Let's say electric field lines are there, electric field line, these continuous curves are there, and the tangent to it gives the direction of electric field. We have already studied this. And this angle is theta, charge is Q. Let's take a very small portion, dr. Dr we have taken, this is a small portion taken on the electric field. Now, work done. Work done is what? From your lower classes, from your 11th standard also, you must have studied what is work done. So work done is basically force into displacement, force multiplied by displacement. Force is also written as charge multiplied by electric field. So work done becomes what? Force multiplied by displacement, that is dr. So dw becomes QE dr. And since it's a dot product, you write cos theta. This is how it is written. This is the definition of work done. According to definition of work done and according to the formula that we have studied. This is how we write it. Now see, electric field, we'll solve cos theta at the end. One more definition of work done is what? One more definition of work done is that it is multiplication, or you can say product of charge and potential. This is from your lower classes which you're already aware of, and this is from this chapter, potential chapter. Work done can also be written as charge multiplied by potential. So I can equate both these work done. So this can be written as E dr is equal to QE dr is equal to, from both these equations, I can write what? QE dr cos theta. Cos theta will be 1. I write cos theta. Theta will be 0 degree. So cos theta 0 will be 1. See how? We are moving from, let's say, point A to point B. In this direction we are moving, and electric field also in the same direction. So angle between the electric field and dr is what? 0 degrees. So cos theta is 0, cos 0 is 1, and we get it as QE dr. This is equal to what? Q dV. So QQ gets cancelled. E is equal to dV by dr. Now understand this result carefully. Understand this result. See, electric field is dV by dr. There are two statements clearly given in your NCERT textbooks which do come in your board exams. Electric field is what? Potential rate of change of potential gradient. Whenever I use the term rate term means anything that gets divided by time or changes with respect to time. For example, you people must have studied in your 11th standard velocity. Velocity is what? That is rate of change of displacement. Why? Because velocity is written as distance divided by time. Whenever anything gets divided by time, we call it as rate of change of anything. Rate of change of velocity is acceleration. But anything which gets divided by position, anything that gets divided by distance, length, or position means it changes with respect to distance. Then we call it as gradient. So this is actually potential gradient. This is potential gradient. E is equal to dV by dr. Now we add a negative sign. When we derive it, no, at the end we add a negative sign. Now, reason for adding this negative sign, this has a lot of significance. Why do we add this negative sign? First point was this, that electric field is directly proportional to the potential. Last line, yes, I'm repeating this whole thing. See, whenever anything gets changed with respect to distance or position, we call it as gradient. So there are two important things. First point is electric field is directly proportional to the potential gradient. Means E is equal to dV by dr. Secondly, we add a negative sign. Now, why do we add a negative sign is your important second point. Significance of negative sign. Both these points are given in your NCERT. Significance of negative sign. Basically, this shows that electric field is along the direction wherever potential decreases. I'll write the statement first. Electric field. Electric field is along the direction where potential decreases. For example, let's say this is A point, this is B point. This is 5 volt, this is 2 volt. So higher voltages at A point, 5 volts is there, and lower voltages at B point, 2 volt is there. So direction of electric field will be where? Where potential decreases. Means direction of electric field will be pointing towards B, where 2 volt. That is why we add a negative sign to show this direction. That electric field is in the direction where potential is lower. That's why we have these 2 points with us. Now, if you look at these points, no, this point E is equal to minus dV by dr. This is your very important equation. dV by dr. dV means change of potential. This basically means change in potential. Now, if voltage is constant for your potential, this is constant somehow. If V is constant by any chance, so what will happen? No change will occur. Let's say V1 value is 2 volt. Final value is also 2 volt. What will be the change? There won't be change. It means change in potential will be 0. That is dV will be 0. So electric field will also be 0. So when does electric field become 0? When your potential is constant. When your potential is constant, then your electric field becomes 0. So apart from this, we have few differentiation terms. But I think before that, you note these points. Then we'll do partial differentiation. If you have how to solve partial differentiation, or basically these. So first note down these. If you have any queries, text me or unmute yourself and ask me. This is one important relation. 2 points are there to remember. Partial differentiation, I'll teach you with the help of examples. So first note down these. Done the writing part? Okay, Zaid has written. And what about you both, Rifat and Wafia?
Yes, ma'am.
Done? All okay, okay, Rifat. Now see partial differentiation. So differentiation, you people already know how to differentiate. Partial differentiation is utilized in this formula. E is equal to minus dv by dr sometimes. So I'll tell you how to get the partial derivative. Basically, partial derivative occurs if you know the main formula. No, main formula is what? E is equal to minus dv by dr. This is the main formula, where dv by dr is what? Potential gradient, that is change of potential with respect to position. If E is calculated along x-axis, it is written as minus dv by dx. If it is calculated along y-axis, that is written as minus dv by dy. If it is written along z-axis, it is written as minus dv by dz. And the net electric field, this is given by Ex plus Ey plus Ez. This is the total or the net electric field. Now, partial differentiation, this is the normal differentiation which you people are already aware of. Now, what is partial differentiation? Partial differentiation is written in this way. If you ever see this delta V by this delta X, Ey is equal to minus del V divided by del Y. Or if you see minus delta V over del X. This symbol, if you see, this is called as partial differentiation. Now, how to solve it? We'll do with the help of numerical only, because without aid of numerical, this won't be clear. Let's say V potential is given to you as x square y z square, and you have to calculate the electric field. You have to calculate the electric field. So now, how will we use partial differentiation? See how to use it. When we are first calculating along Ex, Ex means differentiation with respect to x. Here, your other two terms, what are the two terms? Y and z, these become constant. They act as constant, as if they were constant. So how to differentiate? You have to now differentiate x square yz over dx, keeping in mind that x square is a variable and yz, these are your constant terms. So in differentiation, if you have constant term, what's the rule? The constant terms are brought away from the whole term and they get multiplied. For example, if you have 3x square, you take 3 separate and then you take 2x separately, and then you multiply. Similarly, now for you, yz square, this is a constant. So yz square will come out automatically. On what is left to you? X square, differentiation of x square. X to the power 2. So 2x. 2 will come out, x to the power 2 minus 1. This is the general rule of differentiation. X to the power n is there, no, that becomes nx to the power n minus 1. So if it is x square, it becomes x to the power 2 minus 1, and 2 comes out. This is Ex. Ex, this is Ex with a negative sign, because this is a negative sign in your formula. Z square, because in the question it is given to you z square. This is already given to you in the question. So if z is a constant, z square will also be a constant. All right. Now, Ex, let's see Ex. V is equal to x square y z square. So Ey. Now, when you are partially differentiating y, now y is getting differentiated. So what will act as a constant? Your other two variables. Now x, which was a variable in the previous case, Now x and z, both of these act as constant terms. So what will happen? X square, z square. What is the term given? X square, z square. No. So now see, in the main formula, x square is a constant, z square is a constant. So both of these terms will come out. And what is left? Dy by dy is left. So that is 1. So you have x square, z square with a negative sign. Why? Because y is left, no? And if you differentiate dy over dy, that is 1. So we have got y-axis. X, z is constant. Yes, x and z is constant. I have written x, y. Okay, sorry, z. Yes, right. X and z are constant. Thank you, z. X and z are constant, not x and y. X and z are constant. So x and z have been separated. So x square, z square was given. Dy over dy is 1. Now Ez, when we are differentiating Ez, now other two terms will be constant. So this time x and y, both these terms will be constant. So first eliminate x square, y is constant. It means x square and y will be there. What is left? Z square. When you differentiate z square, you will get 2z. So multiply this whole term by 2z minus. All right. So how is the net electric field given? Net electric field given is with the help of this. Ex vector plus Ey vector plus Ez vector. You will get questions in this way only. Variables will be given. Constant terms separate the constant terms, and whatever are left, just multiply and differentiate it normally. So Ex came out was Ex, let's see, Ex was coming minus y z square 2x. It was minus y z square 2x. So we'll put I cap because it is x-axis and we are considering vectors, so we have to put it. Plus, what do we have? Y, no? Y is minus x square z square. So this is minus x square z square with j cap, as this is y-axis. Then for this we have z-axis, we have minus x square y to z. And we'll put k cap just to show that this is a vector quantity. Clear? Now how questions can be modified in your exam? It can ask you calculate the electric field. It can ask you calculate electric field at 1, 1, 1. It means you just have to put x equal to 1 in this, y equal to 1 in this, and z equal to 1 in this. So you will get a finite value of electric field. This is how the question can be modified. Clear? Start noting it down wherever you get stuck, ask me. This is how to perform partial differentiation. Rifat and Madiha, are you prepared for the test? I told you, no, electric field test we'll be having the whole chapter. Madhya, you people have given your exam, so you people must already be prepared with the chapter. Exam is over. So electric field and charges, electric charges and field, that chapter you'll be able to handle, Madhya?
Yes, ma'am, I will.
You will be. And Rifat, prepared? Today, Rifat, were you absent in the last class? In the last class, I had announced about the test. Electric charges and field. Only 2 questions are there. Don't worry about the test. No, electric field and charges you already have. A potential, only potential. Okay, 2 questions are there. You will be able to handle it. Right now only, after the class, Zaid and Wafia, since they have not done it, so they'll leave early. You both will stay. You can give the test. Very short test is there. Hardly 15 to 20 minutes will be taken. So within the class itself, I'll conduct. Okay, so note it down. So by now, I think most of you must have written it. All right. Now, Zaid and Wafia, just have a little patience because potential, we are almost at the end. Equipotential surface is one topic and potential energy is one topic. So it might happen that in the middle, you won't be able to relate to things because previous topics have not been covered. Just have patience. From the next class or 1 or 2 classes after, we'll be starting with capacitance because we are almost at the end of potential. Capacitance is a completely new topic. From there, you will be totally able to cope up. All right, and potential and electric charges and field, that backup you'll get. All right, so if you are not able to understand anything in the middle, ask me. If even if still you're not able to understand, just have patience, you will be able to understand it, because the topic that we are starting now is equipotential surfaces. So equipotential surfaces, I have written few points prior only because these are certain, they have certain properties. So all those properties I have written it prior. Now, equipotential, what does it look like? Equi means equal, potential means potential. So equipotential means equal potential. So any surface that has equal potential all around, that we call it as an equipotential surface. Let me show you this. Let's talk about a sphere. Let's say this is a sphere and radius of the sphere is capital R. All right. Now, at this point, if I tell you people that potential is 2 volt, for example, I've told you, then I'm telling you at this position, VB, this is also 2 volt. At this point, VC, this is the potential is again 2 volt. So it means the whole potential on this sphere, this is what? This is 2 volts only. VA is equal to VB is equal to CVC, which is equal to 2 volts. Then I can call this sphere as an equipotential surface. All right, this becomes an equipotential surface. If the potential remains the same on any surface, if the potential remains the same, then we call it as an equipotential surface. So this is a very easy definition. Potential constant everywhere, you call it as an equipotential surface. So surface at which every point has same potential. So for example, this random figure ACB, if all the potentials are equal, then I can call this surface as an equipotential surface. Now there are certain properties of equipotential surface. Those I have written prior, so that because this is a very short and easy topic and only these properties are asked in your exam to write it down. So that's why I've written it prior. Potential at every point on the equipotential surface is same. This is the very first property, and that's the definition, obviously, definition of it also, that potential at every point, this remains the same. So for example, all, let's say VA, VB, VC, all these points have the same potential. So this is the first property. Second property is what I was telling you when we were discussing potential right now, electric field. If potential is not changing, then change in potential will also be zero. And we have one more definition of change in potential. Other definition of change in potential is delta. Another definition of work done is charge multiplied by change in potential. So if your change in potential is zero, your work done also becomes zero. This question comes a lot in your examination. Then what is the work done on an equipotential surface? Work done of an equipotential surface or work done on an equipotential surface, this is zero. Reason, change in potential is zero because potential is constant everywhere. This is the second property. Then you have the third property. This is also an easy property. It says that electric field will always be perpendicular to the equipotential surface. If I say this is an equipotential surface, then electric field will always be perpendicular to it in this way. This will be the direction of electric field. Electric field will always be perpendicular to it. Work done depends on equipotential. Work done depends on potential. not equipotential. Work done depends on potential. And since your potential means change in potential, work done depends on your change in potential. That we'll see in potential energy also. So change in potential is 0. So that's why your work done was coming 0. Work done depends on change in potential, not equipotential surface, because there isn't any work done on the equipotential surface. So in case of equipotential surface, you should remember that work done is 0. The second point says this. Clear, Zed? All right. Now, electric field is what? Electric field will always be directed perpendicular. So it can happen in your examination that you are given any figure and you are asked to draw the direction of electric field and you are told that this is an equipotential surface. So what to do? Just drop a perpendicular. That will be the equipotential surface. Now, the fourth point is very easy. Fourth point says what? So this was the third point. Electric field is perpendicular to it. Now, fourth point says if equipotential surfaces are closer, they are kept closer to each other, then we say electric field is strong in that region. And if equipotential surfaces are kept apart, means at a certain distance within them, then we call that equipotential surfaces are, the electric field is weaker. So just by looking at the equipotential surfaces, no, you can easily figure what is the strength of electric field. Is the electric field strong or is the electric field weak? So if the electric field is stronger, then equipotential surfaces, these are just kept stacked to each other, parallel. Parallel, not even parallel, means closer to each other. For example, in this example which I have written, these two regions are there. So you can easily, with the help of this, you can easily figure out that this is closer, this is weaker. This equipotential surfaces are closer. It means if equipotential surfaces are closer, then electric field will be high in this region. And since equipotential surfaces are far apart from each other, this shows that electric field will be weaker in this region. So this is another property of it. Now, these are 4 properties of equipotential surfaces that you should remember. Equipotential surface definition, that means potential remains constant all over the surface, equal potential all over the surface, then we call it as a equipotential surface. Since potential is constant, change in potential is 0, there is no work done on equipotential surface. Direction of electric field is given by dropping a perpendicular on the equipotential surface. And if equipotential surfaces are kept closer to each other, that shows stronger electric field. And if they are kept comparatively far away from each other, that shows weaker electric field. These are 4 properties. Now, apart from this, you can get to draw equipotential surfaces for an isolated charge. See, if you have an isolated charge, no, plus Q, just keep on drawing the circles, concentric circles. So equipotential surface for isolated point charge. This is given by concentric circles. It can give you, rarely this question comes to draw for an isolated point charge. Then if you have 2 positive charges, see 2 positive charges or 2 negative charges are there. And then you have to see 1 positive or 1 negative. Now, if 2 positive charges are there, no, or 2 like charges are there, equipotential surfaces are closer at this end, you can see. And they are at a certain gap at this end. Here they are closer. But if this is the case of a dipole, for those people who are not aware of dipole, especially Zaid and Wafi, dipole is basically 2 charges which have the same magnitude, but their signs are opposite. Like plus 2 coulomb is one charge, then minus 2 coulomb will be another charge. If plus 4 coulomb is one charge, minus 4 coulomb will be another charge. This we call as a dipole. So if one positive charge is there, other negative charge is there, then these dipole equipotential surfaces are closer at this end. And these are at a certain gap far at the other end. So this is the comparison. If 2 like charges, even negative charges, this is valid for negative charges also. If minus Q and minus Q are kept together, then equipotential surfaces will still be closer at this end. And they will still be far away at this end. They'll be closer at this end and they'll be far away at this end. Like this. This is how you will draw, same for negative charges. But if it's a case of dipole, means 1 positive, other negative, then closer is kept towards their meeting line. All right. And then you get electric field for uniform and non-uniform. See, if you have to draw electric field for uniform equipotential surfaces, what is meant by this? Understand it. This is very easy. Uniform equipotential surfaces means all the equipotential surfaces are kept at a same separation. Means if this separation is 5 centimeters, this separation will also be 5 centimeters. Again, the next separation will also be 5 centimeters. So uniform equipotential surfaces are there. This is how you will draw electric field. If non-uniform equipotential surfaces are there, means, see, you can notice this is a huge gap. Let's say this is 10 centimeters. This is a smaller gap, 5 centimeters. So if non-uniform electric field is there, how do you draw the equipotential surfaces? At random distances. If uniform electric field is there, then equipotential surfaces are drawn at a certain specific fixed distances. All of you, first tell me, write down in the chat box, have you understood it or not? Any difficulty in any point, just ask me. And start noting this equipotential surface at whichever point or property you get stuck. Now just text me point number 1. Repeat point number 1. I'll repeat it. Third point of property or the figure to draw it, this one, dipole, or this figure to draw it? Point number 3, dipole, no? Please repeat third point, not this one, no? Okay. See, these points can be understood together. Point number 2 and point number 3 can be understood together. If 2 positive charges or 2 negative charges are there, then try to, whatever concentric, I have told you for isolated charge, how do we draw? Just hide this. Don't look at this. This is how we draw for isolated charge. If 2 charges are there, then those concentric circles are closer at the away end, means where the charges are not meeting at the line, away end. For dipole, they are closer at the joining end. Means that equipotential surfaces become closer and show the strength of stronger electric field, because obviously both of them will attract each other. You people know both of them will attract each other. If they attract each other, electric force is strong, electric field is strong within them. If electric field is strong, how do we draw the equipotential surfaces? We draw them closer. That's why we have drawn them closer here. But here, both of them are repelling each other. So it means forces are weaker. Both of them are repelling each other. Electric field is weaker. That's why in this region, we have drawn the electric field part. Okay, sir. Are you all added on the WhatsApp group, new students, Zaid and Wafia?
Yes, ma'am.
Okay, okay, Wafia. And what about you, Zaid? Are you added on the group? Boys group is different. All right, Zaid. Done. Writing part is done. Madiha, Rifat, Wafia, Zaid.
Yes, ma'am.
Madiha done. Rifat, what about you? Rifat, Zaid, Wafia?
Yes, ma'am.
Okay, Zaid is also done. Rifat is also done. Fine. Fine. So, see, in the next class, one last topic, potential energy is left from potential. And then we'll begin with capacitance. All right. So, Madiha and Rifat stay because you people have to give the test. Wafi and Zaid, it's your wish. If you are familiar with electric potential concept, then you can give the test. Otherwise, it depends on you. All right. Yes, Zaid and Wafia, you people can give it later. It's okay because we have not done it together. No, Rifat and Madi, I think you will be able to handle it. Direct questions are there. You have to calculate electric potential and derive an expression for electric potential due to point charge. Leave this question one. Just do answer two and answer three. Okay, Zaid. What about you, Wafia? Are you giving this test or what is your status? Okay, Allah Hafiz. Yes, Wafia, you're saying something?
No, ma'am.
So are you means you have you done this topic earlier, electric potential? Will you be able to give these two questions, answer two and answer three? If yes, then you can give the test along with both of these. Otherwise, it's your choice, open choice. Just tell me.
Uh, can I do another day?
At the end means after you've studied, no?
Yeah.
All right. Okay, fine.
Thank you, ma'am.
Okay. Again, repeating. No need to do question one. Just do two and three. Do both these questions. Madhya, whatever is your answer you're getting, just write it in your answer sheet. Then click the picture of the sheet and convert it into a PDF and upload it in on the WhatsApp group in which you must be added. Whatever answer you are getting, no, just write it. Means this is a subjective test, no? So obviously you have to show your calculations and working.
Okay.
Okay, Rifat, I've received. Fine, you can leave. But yeah, how